Hello everyone, I'm Jack Sullivan and I'm currently a senior physics major at the University of Massachusetts Dartmouth, working under Dr. Robert Fisher. My research focuses on computational astrophysics and specifically modeling Type 1a supernovae. So Type 1a supernovae are thermonuclear explosions that occur when a white dwarf star gets massive enough to exceed a threshold called the Chandrasekhar mass, which is a mass around 40% larger than our Sun. At this point, all the forces within the white dwarf can't resist the gravitational pull of all the accreted material, and the star crushes it in on itself and detonates, resulting in a supernova. Type 1a supernovae are important astronomical events since they're essential for measuring the expansion rate of the universe. They always explode with a constant luminosity because of that constant mass they explode at, meaning that they only dim based on how far away they are. This allows us to use them to determine distance scales around the galaxy. They're also important because these supernovae are a major source of elements essential to life on Earth, such as iron, nickel, and silicon. Although Type 1a supernovae are extremely important, much about them, including their explosion mechanisms, is still unknown. There are two ways to cause a Type 1a supernova that are known. One way is called the single degenerate scenario, and it's when a white dwarf accretes mass from a much larger star, such as a main sequence star like our Sun. The other scenario is a double degenerate scenario, in which two white dwarfs orbit each other, eventually colliding. After a supernova occurs, we're left with a supernova remnant, which can also be observed by telescopes. Based on the light spectra from these, we can tell the fractions of different types of elements within the remnant. The research my graduate student mentor and I are focusing on is with the single degenerate scenario, and specifically on a supernova remnant called 3C397, which was thought to have been created around 1,000 years ago. On the left side, you can see a NASA visualization of it, and on the right side is a picture from the Japanese Space Agency of the spectra. Based on observations from the XMM Newton satellite and a paper done by our collaborators in Japan, it was found that this specific supernova remnant was unique because it had an abundance of iron group element clumps in its southern region. You can also see that in this picture as well, where the blue there is chromium on the bottom. Our goal is to create simulations of a white dwarf explosion and tweak the initial conditions of the white dwarf to get an end result that's similar to the observed results. For our research, we simulated 3 models of this explosion with different initial conditions. To simulate them, we used the adaptive mesh refinement code Flash4 to map out the morphology of the explosion. The first model is a deflagration to detonation explosion mechanism. This is when a subsonic deflagration rises through the white dwarf and then causes a supersonic detonation once at the surface. This model has a higher density, which is normally associated with Type 1a supernovae that create higher amounts of iron group elements. The next 2 models are both pure deflagration models, where there is a deflagration at the center of the star that just completely detonates. One is high density and one is low density with a different carbon-oxygen ratio. The explosions are simulated out to 6 seconds when the remnant is in free expansion, which means there's no more acceleration and it's just expanding at a constant velocity. This means whatever you see at later points will be the same as what you see at this point, but just bigger. We also use something called Lagrangian tracer particles, which are just small points of constant mass that follow the hydrodynamical flow of the model. These give us information about the remnant at any time step as it evolves, including information such as temperature, density, at whatever point the particle is at. So moving on to our results, our first plot is a density plot of our deflagration to detonation model. All of those visible points on the plot represent the particles that I was talking about, and from those we get the densities of iron and chromium. So what we're looking for in the model right now is 2 things. We're looking for that clumping of heavier elements, like from the original satellite image, and we're looking for that more asymmetrical amorphous shape. So here you can see that the explosion actually leaves a lot of the heavier elements near the center of the remnant, and it blows away a lot of the lighter elements on the edge. It doesn't really have that clumping that we're looking for, and it's not symmetrical, but it doesn't have that amorphous shape. So this model isn't exactly in support of the observed results. So in this case, this is our low density pure deflagration model, and it does have that amorphous shape that we're looking for, but it doesn't have that clumping of elements. They're more evenly spread out throughout the remnant. So our last model is the high density pure deflagration model. In this one, you can see that there actually is that clumping of heavier elements that we're looking for in the bottom, and it also has that asymmetrical amorphous shape. It's still very smooth, but it's not as smooth of a curve as the deflagration to detonation model. So this model actually supports the observed results the most. So this is all the work we've done so far, and the next steps that we're undertaking are to calculate the nucleosynthetic yield to actually get the numerical values of the elements within the remnant, as well as changing the metallicity to get different results. So the conclusion of our work so far is that our findings support the idea that high central density white dwarfs can lead to an abundance of iron group elements, and that a high density pure deflagration model best supports the observed results of supernova remnant 3C397. Because in this case, we can't prove anything, we can only support the idea. If you have any more questions, I'd be happy to answer them at the conference. Thank you.